Now, connected with that, there are some additional components, and one of these is referred to as Henman's size principle. And this is really important, and this helps explain why we see that force-velocity relationship we've already been referring to. Because as I've written here, there is what we refer to as a hierarchy of recruitment of motor units. So we recruit small motor units first, which are low force ones, through to the fast motor units. So what do we mean by small motor units? Well, small motor units would be slow twitch fibres. Smaller. Remember, we were recruiting for the same fight, for the same nerve. We were only recruiting, remember, 1/3 in the schematic we saw from Comey, 1/3 of the fibres we were recruiting in our fast fatigable. So what we know is that the slower twitch fibres, the smaller fibres, are going to be recruited first. So the small motor units are innervated by small but easily excitable motor neurons. They can be activated very quickly. And the fast motor units are innervated by motor neurons with higher excitability thresholds. It takes more to innervate them, so we need a greater neural input to generate force from those faster fibres. And so what you get is a modulation in force. And you basically, this is really important because think about it very logically. There'll be no sense in us recruiting all the muscle fibres all the time. There's no point in recruiting fast twitch fibres if we're doing an activity which is either requiring just slow force generation or low levels of force being produced. So we end up recruiting slower twitch fibres. It's only as the amount of force that we are trying to produce starts to increase that the number of motor units that we recruit also start to increase. Now, this is really important. That doesn't mean that we move from slow twitch to fast twitch and that's it. What it means is that we have what we call a summation of force, that the fast twitch fibres are recruited as well as the slow twitch fibres. So remember, the slow twitch fibres are not really fatigable. They are, but in the grand scale of things, they are fatigue resistant. So it's not like they are going to have run out of energy. It's not like they're going to have lost the ability to generate force. They will still be used when we are trying to generate more force. What we're doing is we're recruiting these faster, larger units on top of the slow twitch fibres. And the net result is that what we start to be able to do is increase the amount of force. So we never recruit fast twitch fibres when we've got to generate small amounts of force or where we've got to have slow muscle actions. And so you suddenly start to think, oh, so this explains a lot of what you're seeing with force velocity. If the amount of force being produced is low, the velocity of shortening can be high. Why? Because slow twitch fibres have got very quick excitability. They're innervated very, very rapidly. Fine. If I need to produce really high amounts of force, I've probably got the slow twitch fibres which are involved, absolutely. But I now need to recruit these fast twitch fibres, these bigger units. They take more of a neural kick to innervate them, but they will generate more force. But remember, they are fatigable. And what you can see here is a really nice example of this. It looks slightly confusing in terms of the data, but actually it's really nice. So what you can see on the left-hand side of this panel is the percentage of the MVC. The MVC refers to the maximum voluntary contraction. So what they've done here is they've done percentages of MVC using what are called isometric contractions. Next to that is the N. Don't worry about the N, it's just the number of participants or recruitments that are taking place. But the key is the amount of force, which is in the third column. So the force here is being measured in newtons. And what you can see is as the percentage of the MVC, remember that under an isometric contraction, you're generating a high amount of force. That's fundamentally important to understand. So you can see that from 5%, you're going up from 27.7 newtons to 470 newtons at a full MVC. And even if you go to 50% of the MVC, you're up to about 268.5 newtons. Right, so why is that so important? Well, let's have a look at a little bit across. You can see the mean firing rate. So this is the rate at which these fibres have been recruited. There is a change, right? You can see there is a gradual increase in the firing rate. And that is because we're having to recruit more fibres. Remember, we're going from, if it's low force, we're going to be using our slower twitch fibres. So the firing rate is relatively low. We don't need to recruit large fibers very quickly. But as the amount of force starts to go up, we need to recruit the fibers more quickly because we need to be able to generate that force. But can we see this in action? Well, we can. Remember that what we're talking about in our previous example here is the size of the units. So if you look here and you look at the second to last column, you've got what is referred to as the MUAP. And what this basically refers to, it's the size of the muscle. So this is kind of their abbreviation for the size of the muscle. It's the area. And what you can see is quite significant changes that, remember, when we are doing a low amount of force generation, we're recruiting slow motor units, which are small. So we're going from about 323 in terms of the micro units in this example here. But by the time we get to the MVC, what we've done, or the 100%, sorry, the MVC, we've summated, we've added the slow twitch fibers, we recruited more slow twitch fibers. Look, we've gone from 5 to 10%, we've gone from 323, it's gone to 305. It's a little bit of an anomaly probably in the data that you're seeing there, because you've gone from an N of 8 to an N of 78. But if you look at 20%, we've gone up to, we've near enough doubled it. So we've gone from 305 to 599, near enough doubled it. If we go from 20 to 50%, we've gone from 599 to 1,156. If we go from 50%, we've almost doubled it again. We've gone to 2,332. In other words, the area, the total area of recruitment has increased. We've gone from recruiting smaller units. We're adding the smaller units, we're adding the core and more, but we're starting to recruit larger units, and therefore the total area, the Henman size principle here, motor unit size, has increased. We've not only just got the slow twitch fibers, we've added on these faster twitch fibers. So the net result is the amount of force we're producing increases. And you can see this really nicely here. It's from the same data set, but it's quite nice seeing this kind of graphically. So you've got the area, which again reflects the size of the motor units on the x-axis, and the amount of force being produced on the y-axis in newtons. And you can see, and bear in mind that a lot of this is a function of the amount of samples that are being collected, but what you can see is as the area, the motor unit area, the amount of fibers that are being recruited increases, look at the change in the amount of force being produced. It's a lovely linear relationship that you're seeing there. That, you know, where we've got, for example, an area of, say, about 1,000, you can see that they're producing around about 200 newtons. But if we go to the equivalent of, let's say, 2,000, we're going up to about 300 newtons. So you can see there's a proportional increase in the amount of force being produced to the amount of motor units, and therefore the amount of muscle mass that is being recruited for the generation of force. And in fact, if we look at this really nice statement from Roger Inoka, which was published not that long ago in Perspectives in Medicine, he writes this: the force exerted by a muscle during a voluntary contraction depends on the number of motor units that are activated, which we've been referring to, but also the rates at which these motor units discharge action potentials. The action potential is basically the neural signal. These two properties are known as recruitment and rate coding, respectively. Over most of the operating range of a muscle, the force it generates is controlled by the concurrent changes in recruitment, that's the Henman size principle, and what is referred to as rate coding. So what you can see here is a really good example of this. So you've got different examples. It doesn't matter which one you pick, whether you pick MU1, MU100, MU200. But what you can see here is on the x-axis the discharge rate. So that is the rate at which the action potentials are discharged. On the y-axis you can see the rate of force development. And what you can clearly see is if the rate of discharge starts to increase, that's how quickly we send the electrical signals to the muscle, the amount of force we start to produce also increases. And this is really important because it's not just about how many motor units we recruit, which is Henman's size principle, but it's also about how quickly we can keep recruiting those fibers. And so you have what is called the recruitment, that's Henman's size principle, but rate coding, which we're about to explain in a little bit more detail, which is basically the notion of how quickly we can keep recruiting the fibres, the discharge rate, how quickly that electrical signal can come through the CNS, through the motor unit, and innervate the fibre to generate force. And the more quickly we can repeat that process, the more quickly you're going to generate force, and more force you're going to be able to generate. And that's what you can see here. So you can see the size principle, which is the solid line. So that's Henman's size principle that you can see there. And quite clearly what you see is we're producing low amounts of force, and therefore we've got low amounts of force, we'd have low amounts of fibres being recruited. But then you've got rate coding. And rate coding is basically how quickly that force is, how quickly those fibres are being recruited. And you can see that the two are coupled together. That not only is it about just recruiting more fibres, but as we start to generate force, we've got to be re-innovating those fibres more quickly. So it's a fundamental combination of the two. If I want to generate force rapidly, I've not only got to be able to generate fast twitch fibres, because they're the ones that produce more force, but I have fundamentally got to be able to recruit them at a fast rate. It's no good being a Usain Bolt, for example, or a Dina Asher Smith, and being in a position where I'm going to try and sprint 100 metres and I've got lots of fast twitch fibres. If I can't keep recruiting them at a fast rate, it doesn't matter how much force I can produce, I can't produce it fast enough. So it's a function of the size principle and the rate at which we innovate those fibres, which fundamentally dictates the force-velocity relationship and therefore the amount of force that we are producing. And that is fundamentally what we're trying to ascertain when we're assessing both strength and power in a muscle. And in fact, if we look at this statement here, which was published actually in EJAP not that long ago, it's really important. The magnitude of the activation, and hence the force produced by a muscle, depends on the number of motor units activated. Okay, so that is really important. That's Henman's size principle. And the rate at which the motor neurons discharge action potentials, rate coding. So how quickly can we actually innovate the fibre? The recruitment order of motor units during rapid contractions is similar to that observed during slower contractions and follows the size principle, i.e. low threshold units are recruited before larger ones. So in other words, what we're saying is we don't have to have fast contraction rates if we're going for slow contractions. We don't need them. We can recruit slow twitch fibres. Slow twitch fibres can generate low levels of force because we don't need to generate high forces and we don't necessarily need to generate fast. But as we start to increase the amount of force we want to produce, and also we probably want to increase the rate at which that force is generated, we not only have to recruit more motor units, we also have to get them to discharge the action potential, that is the neural signal, more rapidly. So fundamentally, you have to recognise it's a function of both Henman's size principle, that's recruitment, and the rate at which we can recruit the fibres, which is rate coding.